So we'll forge ahead. If people want to stay, that's great. I'm certainly going to stay. And I'll do this regardless of whether people stay or not. And so this is kind of the culmination of what we're attempting to show in terms of the linkage. So it's an appropriate linkage, because it's a very interesting linkage, which is the essence of many problems in geomechanics. This linkage would affect hydraulic fracturing, it's a consolidation problem, and so it's this linkage between hydraulic and mechanical behavior. And so the essence of it, as you can imagine, is that you have a solid system, and you have fluids flowing in that solid system. The solid system we have is a static one, and the fluids flowing in them potentially change the pressures, and the result of those changes in pressures, deformation occurs. Deformation occurs because of effective stresses. The law of effective stresses, I guess, is the key, and basically says that total stresses are equal to effective stresses plus some coefficient times port pressures. And so the total stresses would be the stresses you apply on the system. The fluid pressures would be in the system. And the difference between these total stresses that you apply versus the fluid pressures that are in the system is the effective stress that it feels, because it has the fluid pressures acting against it. And those effective stresses are important because what scales with effective stresses are deformations. We haven't said this, but these are effective stresses that cause the deformations. So it's effective stresses that cause deformations. And also, if you're looking at failure, if you look at, for instance, shear stress is equal to friction coefficient times stress, normal stress. If you look at a block on an inclined plane, there's a normal stress, sigma n. There's a shear stress that resists this, tau. Then this normal stress is an effective normal stress. So it controls deformations and it controls strength. So it's effective stress that we're always interested in. If we're looking at solid mechanics problems, as we did in the last session, or one session back, then we're looking at stresses. We haven't said whether they're effective stresses, but they are effective stresses. We haven't said they're effective stresses because there's no port pressures involved. And so that's the key. So that's the key observation, I guess, in all of this. The other thing is that if we come back to look at what we've talked about so far, then you can imagine that we have looked at the condition where we have, I don't want to do that. What do I really want to draw? We could think of this as our geometry, and we could think about fluid flowing through this and stresses being applied on it. But more importantly, the systems we've talked about are systems of flow, which have been given by K H dot plus, so not H dot, it's wrong. KH plus S H dot equals Q. These are matrices. And mechanics has been F equals KU plus 0, 0. Right? That might be one way to. This is the mechanical part, this is the fluid part. And so if you think about these and want to put them in the right location, then how do we do that in the framework of this way of thinking about it? I guess one thing is that we know that heads are equal to pressures divided by unit weights. And we've always worked in heads in the things that we're doing. But for instance, we could divide all of these by 1 over the unit weight of the fluid. And if we do that, then we'd have something which would look more like, I guess, KFP plus storage P dot pressure is equal to 1 over unit weight times Q, I suppose. These would still be vectors, and this would be a scalar, right? So, and the reason for writing them that way is because we like to maybe put them in the right framework here to be able to understand what's going on. So what do we have to do that? Well, let's take the derivatives. Let's note that if we take the derivative with respect to time of displacement, for instance, this is equal to u dot. The displacement with respect to time of forces is equal to F dot. And so what we could do is we could take this derivative of this, just operate on this, to merely get, so if we operate with this dt operator, then we get a rate of change of displacement as a function of a rate of change of force. And so now what we can do is we could start putting them in the right place. So we have components here which relate to displacement rate. So this is S11 in this terminology. This is this. We have this term here which relates to pressure. So this here is R22. So we have this, and we have this. We have something that operates on pressure change. So that would be this. And we have this term on the other side with maybe a component attached to it. So that's what we have. And so the one thing you notice about all of those is that they all exist on the leading diagonal of each of these relationships. In other words, they're on this diagonal and they're on this diagonal. And if we don't have any off-diagonal terms, there's no linkage between them. They don't see each other. They operate completely independently. And so there's pressures defined only here and displacements defined only here. So if we want them to talk to each other, we need to figure out how to get pressures into this case and how to get displacements into this case. And if we do that, then we'd be able to figure out exactly what the forms of these linking matrices are. So that's the essence of what we're trying to do. Yes, go ahead.
For in law equation, we divide total equation by gamma n.
Right. This
Gamma fluid.
can.
Below the equation, the pressure head over gamma fluid is equal P.
No, okay. So what we're doing is we are going to, oh yeah, you're right. So this is H is, you have to multiply, right? That's your case? Yeah. Yes. So that's a good point. So this means that if we take head and we multiply both sides by unit weight, then we get pressure. So actually we have to not divide it by this, but we have to multiply it by unit weight, in which this is just this, right? So we multiply both sides by gamma, and then this becomes gamma, right? That's a good point, yes. So that gives us the right magnitude of this. Okay? So the essence of what we want to do is be able to figure out what these cross-coupling terms are. And we can do this in two ways. When we talked about dual porosity behavior, we took the governing, what we thought the governing equations were, And from whether they were second order or first order or zeroth order partial differential equations, we could make the finite element equations from them, and then we could see exactly what that would look like, so we could implement it in MATLAB type of program. Then we just defined the partial differential equations, and we looked at COMSOL to see how we would implement it in there. So let's try and do both of those in the time we have available. And so the first one is to be able to figure out exactly what the governing equations are that make the finite element statement. And so this is the problem, or not the problem. We already talked about effective stresses. And we already said that total stresses are equal to effective stresses plus pore pressures. There is a term here, but let's not worry too much about that. And so this is the law that we need to know because it defines that behavior is controlled by deformation as sigma equals d epsilon, sigma prime, and failure. Let's not care about failure. So that's the essence of it. We need to be able to realize that. Of course, because effective stresses are equal to total stresses, minus pressure, then the significance of it is that when we solve these boundary value problems, you add boundary conditions to these. These are total stresses. These are total forces that we apply. It's only in the interior that we have to define what the effective stresses are. And so in any problem that we're solving, if we only had effective stresses, then we wouldn't necessarily have to, actually would. So these are actually the boundary conditions, but the interior conditions that cause deformation are a function of these individual magnitudes of effective stresses. So what we can do, we could rationalize that from what we talked about previously, that we're going to need to look at the mechanical problem in terms of how that evolves. And we're going to have to look at the flow problem, how that evolves. And we're going to have to look at the linkages between them. And so we'll take care of that. Bit involved, so let me see how long it is. It's not so long, it's 2.5 pages. And this is, yeah, okay. So if we write things out in longhand, in 2 dimensions, we can write effective stresses in terms of stresses in the x direction, stresses in the y direction, and shear stresses xy. I'm just going to write this out in longhand so you know what it looks like, is equal to effective stress in the x direction, effective stress in the y direction, and tau xy. Fluid pressures don't act on shear stresses, just on normal stresses. And minus pressure, pressure, and zero pressure. So this is the effective stress rule in terms of tensor. I guess I'd written it down before. We're interested in changes in this, not necessarily absolute magnitudes. So this delta just refers to changes. And so we can map these if we want. Pressure is a scalar value. It has magnitude but not direction. And so if we write out this tensor of total stresses, which is this tensor of effective stresses, which is this, and then the fluid pressure, which is this, then we need to have an operator on it to make sure that it only operates on the magnitudes of normal stresses. And so this operator is just 1, 1, 0, just a vector. Yes? Oh, you're just... Hello? You put your arm up. You didn't realize? Yeah, I know, you just taking glasses off your face. Okay. And so now we could rearrange this in terms of effective stresses, which is, no, okay. So we can define the constitutive law. We said that sigma equals d epsilon. We've seen this before. I'm calling it E because I think we'll use D when we talk about the permeability matrix. And we need to distinguish between them. So this is our constitutive law. And what we could do is we could substitute this into here. And if we do that, we end up with this expression here. So this is this. This is this. Now with this substituted, and this is this part here. So that's our. So we have an effective stress law written in terms of strains, not in terms of effective stresses. What else? We can now put this into an equilibrium equation. We never defined it as such, but you might remember when we looked at, oops, when we developed the principle of virtual work, what we did was we said that the external virtual work is displacements times forces. Internal virtual work is strains times stresses. These are defined at nodes. These are defined all over the volume, so you have to integrate it. We substitute for the strain relationships, which is epsilon is equal to AU. Which is this. And we manipulated everything else. I guess we also added, what else? Yeah, I guess this is this, and this is this. And so what we then did, we actually put in the constitutive law here, right? Sigma equals d epsilon, but let's not do that. Let's realize that this here can be cancelled out with this here. And now the relationship we have is something that links forces and these displacements. And so in other words, forces and these displacements is just this residual equation here. So it's just the same equation we had before. And actually this is kind of an equilibrium equation. These are derivatives, and this is stresses, and so it takes the derivatives of stresses and makes sure that they balance. But it doesn't matter. We don't need to go into much detail with that. This uppercase A is what we've called lowercase a before, again just to distinguish it because this is for the mechanical part. There's an A matrix when we look at flow, but it's not the same, right? There are different matrices. And so we have this matrix, we have total stresses. Presumably we could substitute this into here, and if we do that we get kind of a long expression, which is A transpose dA multiplied by du. We have A transposed M, which is the part that's due to this. And I guess we have dF. And so we have most of the parts that we need, except what we could also end up doing is we know that we map nodal variables in terms of pressures as equal to shape functions and nodal magnitudes of pressures. And we already have these in terms of nodal values. And so if we make this substitution, then these are nodal values of pressures, and we have a new matrix, a matrix we actually haven't seen before. This matrix is the result of a first order. So this term here is d2p dx squared. This term here is something like v dp dx, or a constant times dp dx. It's a first order derivative. Second order derivative, and we don't have any others. And so if we boil this down to a simple equation, it's something operating on a rate of change of displacement, something operating on a rate of change of pressure, and a rate of change of forces in the system as well. So that's our first expression. So 7 and 8 are the first expressions that we need to define behavior. Okay, so that's the mechanical part. It's exactly the same as the stiffness part right before. This is a stiffness equation. This is the force, but what we've done is we've just taken the derivatives of these. And the new term that we have that we've never seen before is this particular term here. So that's the equation that includes this coupling. And so if we go back to this expression here, we now know exactly what this term is. That's what we have, the first cross coupling. It operates on rates of change of pressure, and it's this magnitude. And so we know what it is. So if we knew what the pressures were, we could add those pressures in, and that would give us the full effect of the fluid pressure effect in the mechanical equation in terms of the deformations that it would cause. But what we'd also like to get is to know how pressures might change and how those pressures might change over time to be able to feed back into that. If we know how the pressures change with time from this other equation, then we know how to be able to solve it. And so we have this, the conductance equation. We have this, the storage relation. We have now an expression which links the effects of deformation. And so what that really is, if you think about it, is if you prescribe some rate of change of deformation on the element, it's going to squeeze it like a sponge. It's going to squeeze the fluid pressure out of it. And so we said already that the terms of this whole equation here, the continuity and flow equation, the term k d2h dx squared is in terms of a mass flux per unit volume. It's meters cubed per time per meters cubed. And so really what this displacement rate would give us would be a rate of squeezing fluid in terms of a volume per unit time per unit volume. And so that's really what it's giving. In the same way that when we looked at the dual porosity term, we had an equivalent exchange term, this term that linked the flow out of the matrix into the fractures. The units of that had to be in volume per unit time per unit volume. This is really the same thing. This is the amount that's squeezed out of an individual element. So let's go and look at the flow equation. So what do? This is Darcy's law. Velocity written in terms of pressures. So this is something like velocity equals k over mu dp dx, which is Darcy's law. There should be a minus sign in there as well, as there is. Let's ignore the fact that there's a self-weight term. Just don't care about it. Just remove it. It happens to have velocities not just in the x direction, but also in the y direction. So that's this. We can use this little del sign to represent this derivative as a vector form. And we can write a conservation of mass term. This is mass in minus mass out. This is accumulation due to fluid compressibility. And this is accumulation due to compaction, if you like. So accumulation usually means stuff that's accumulating inside it, but it could also mean the negative accumulation, right? The amount that's squeezed out. And so you can imagine that there are two effects. The first effect is that you take the sponge and you squeeze it. You know the water's going to come out of the sponge. So that's because it deforms this term here. The second one is if you put water in a closed system and you compress it, so the pressure goes up. And so if the pressure goes up, it compresses. If the pressure goes down, then it must expand and leave the volume. And so you have both of these factors acting. You have an incompressible fluid that you can squeeze the sponge, and the water will come out. Or you could have an incompressible container in which you squeeze the fluid in that container. And if you squeeze it and the volume of the fluid is less, then it has to suck some fluid in to be able to fill it up. So you have both of those features acting at the same time. And so if that's the case, then we have both of these terms. This term here is actually, if we write it out, it is what? This is this. It would be M transpose eta is equal to 1, 1, 0. If you go back one page, you remember that we defined this matrix here. And so we take the transpose of that and multiply it by the strains in the x direction, the strains in the y direction, and the shear strains. We have 3 strains. And so shear strains don't make any difference. Shear strains are like taking a pack of cards and deforming them. There's no volume change in shear. There definitely is volume change in normal compaction. And so we end up with those. And so that's exactly what this means. And if we now substitute Darcy's law into this, we end up with this expression. Let's ignore that. And now, as a result of that, we have this expression here. This is just this second order PDE, which is this. This is just these terms here, where these are strain rates. I guess these are strain rates also here. And this is this final term. And so we can start doing something with them. I think this last step here is trying to do the Galerkin thing, but let's not worry about this, right? You weight it by some magnitude. For a weighting function, you do some manipulation. But let's not do that. Let's skip this step, because we don't care, and figure out exactly what this is. This is the conductant term. So it's going to be A transpose Ka operating on pressures. So this is our K matrix. This is both of these terms are 0th order terms, right? So this term here is going to look something like porosity times stiffness of the fluid multiplied by B transposed B dV. And so this is going to be a capacitance term. This is also the same thing. It's just a constant. So this term here is this. This term here is going to look like this. This whole thing, I guess. Because, you know, it's just going to be 1 multiplied by this. So it's going to be integral. Actually, do we probably have to do something with it first? Yeah, okay, we do have to do something, right? We have to realize, I guess, that, right up here, epsilon is equal to, do we call it AU? Right? This is just the A matrix that we defined before. I think we used uppercase A, right? If I don't remember, yeah, this value here. Is this? We want time derivatives. So we want this and this. We can substitute this it's this term here, right? So M transpose epsilon, we can substitute for this, and I guess we do need to use this weighting factor here. We end up with B transposed M, which is this matrix, and the rate of change. Okay, right. my problem. This is not a zeroth order matrix like this one. And it's not because this is epsilon, which is equal to du dx. So it's actually a first order. This is second order, this is zeroth order, and this is first order. So we can't just weight it by the B transpose B matrix. We have to actually use, substitute into here the fact that epsilon dot is equal to A U dot. So if we substitute into this, if we pre-multiply by this factor here, B transpose, which is this weighting function, this is this weighting function, which I scribbled out. This whole term here is M epsilon, M transpose epsilon dot. Yeah, this is. So this is the weighting. This is M transpose. A U is this epsilon part. So it's getting a bit messy. But the bottom line is, and let's not worry about these other components, is that we have a component that relies on pressure. This is our conductance matrix. I'll move it up so you can see both. This is our storage matrix, which before is what is it? B transpose B dV. This is integral A transpose K A dV. So both of these we've seen before. I'll move it up. And so those are part of the flow equation that are written, as you notice, only in terms of pressures or equivalent heads, pressures and rates of changes of pressures. And our interest in this is now we have this new coupling term, which is this, the role of deformation. So this is the squeezing the sponge and squeezing fluid out of it. And so this last term is this new relationship. And this relationship is integral over the area, B transposed, M transposed, A, dx dy times U dot. So that's it. And so we have a second order PDE for the flow equation, we know that. We have a zeroth order PDE for the capacitance term. And we have a first order equation for the strains, du dx, that squeeze the fluid out of the system. So you can think of it in terms of displacements, which are the nodal variables, but displacements are really representing strains within the system. And so if we take this now and put it back into this previous expression, what do they look like? So this would be, this is the flow part, this is the capacitance part, and this is the squeezing part. So let's label those. So this is R22, this is S22, and this is S21. And so those are the components we need. And so I'm not, yeah, okay. And so those are the expressions. So what we've done, it's probably not all that interesting to delve really deeply into this, but what we've done is we started off with the circle terms. Conductance and fluid pressure storage, written only in terms of pressures, defined only in terms of pressures. We started with a second system that overlaps it, which define a stiffness related to the forces through displacement. Instead of forces, we use displacements rates and force rates, and defined only in terms of displacements, and therefore not coupled to the fluid system through pressures at all. And then through what we've done, we've allowed the displacement equation to include the effects of fluid pressures, now in this expression. So it includes not only displacement terms, but also fluid pressure terms. And in the flow equation, which previously only included fluid pressures, we now have something that includes deformation. And so those cross terms are the linkages that we have. The other interesting thing is, I think it's really interesting, is that the matrix S12 is actually the transpose of S21. So actually this matrix system, this is a stiffness matrix, so this is symmetric. This is the lumped mass system. This is symmetric. These are not symmetric individually, but this overall matrix, if you look down the center line of this thing here, is symmetric on either side, because S12 and S21 are the transpose of each other. So they just switch. So it's actually quite an interesting system that it works out to be that way. I think incredibly interesting that that's the case. And you can show that for yourself. All right. So what we could do, yes, a short thing. So what we could do is we could take those expressions that we have now and we could rearrange it in a slightly different way. So this was R22, S11, S12, etc. These are our S matrices, these are our R matrices, and we can write them like this. I guess I noted this before, that it's symmetric because those are the case. What do? We need to define these time rates in terms of something, and we can do that in terms of the magnitude in the future relative to the magnitude now, or if we're standing in the future, the magnitude now versus the one that came before. So we have this is just du dt, and also dp dt. And actually it's really delta p over delta t. They're finite derivatives, right? Not partial derivatives. And if we substitute both of these into here, we get these expressions in here. We rearrange for the magnitudes of the furthest most in the time in the future magnitudes here. Those would also be these magnitudes here. And we gather terms. And we end up with an equation set that looks like this, I guess. Yeah. And so we know what these individual expressions are. We just end up with revised equations. We've done it already before, so perhaps we don't want to spend too much time doing it here, because I wanted to actually finish off with some other things. And so there's probably enough there. It's kind of complicated, but you can, if you want, you can try solving it in some way. I won't talk about those. But that's the system of equations we'd end up. So that's tracking through things exactly the same way that we did for the first dual permeability example. We define the physics of the system. We know whether it's a flow system and a capacitance part and part that's due to strains. We figure out, just by inspection almost, what the finite element equations should be that would represent that. And we can piece it together into a statement that then, if we wanted to, we could probably put in MATLAB and be able to do something with it. And so that's the way that we deal with it there. So that's one way of doing it. The other way of doing it is to do things in a slightly different way. And I don't have a way of being able to run that in EGEFM. The other way is to do it at the partial derivative scale. And it's not quite so neat to do it that way, because we perhaps don't have all of the background. But maybe I'll just try walking through it, and I can explain what the components are. I suppose, no, actually, in this, the one thing we don't have, as we look back through here, we certainly have a finite element statement or a PDE statement inside the brackets for the flow equation. So we absolutely do have that includes the effects of strains. But if we look at the solid mechanics expression, we really only have the finite element expression from the way we did it. And we don't have the component PDE. But let me walk through this. And what I'd like to do is walk through this and then see if we can make it work in COMSOL, or at least open it up in COMSOL to show what the individual terms should be. So we have these two systems, solid mechanics system, flow system. The solid mechanics system, we said that virtual work internal equals virtual work external. That was the relationship we used. This relationship is the same as the equilibrium equations. Equilibrium equations say that the change in stresses in the x direction with x to be in equilibrium have to be, so in other words, it's saying that if this is the x direction, then the stress that's applied in the x direction and how it changes from one side to the other, if it changes, then it basically has to be balanced by a shear stress in the in this direction, tau. And so if there's an imbalance of the normal stresses in this direction, it has to be balanced in some way by the shear stresses in the other directions, both on this top surface and also on this side surface, right? So you have a pushing in this direction. If the force that I'm applying with my left hand is less than the one that I'm applying with my right hand, then there has to be some shear stress applied on here and some shear stress applied on here to keep it in place. And the physical explanation of that is that if the stress in the x direction, as it changes from my left hand to right hand, has to be directly balanced by the changes in shear stress as they go across on those two other faces. So that's the reason why there's these three terms. The inertial term we don't care about. The body force term we're not going to care about either. Someone asked earlier about that. We know that we can define strains in terms of this. Normal strains are displacement gradients. We know that we can define shear strains in this way in terms of displacement gradients. And we can also define fluid strains as a function of the volume and this is a volume of fluid, change in volume of fluid over the total volume. So just the same as the strain is. So this is delta VF. You can't see it very well. Still can't see it very well. Equilibrium equation. We said that to solve any boundary value problem, we need four conditions. Really only three important ones. Well, you need an equilibrium equation, mass in, mass out, or the equilibrium equation which we have here, which is basically this. We have to have a constitutive equation, and we've never written it in this particular form, but the constitutive equation says that sigma equals d epsilon is the way we've written it. Individually, it looks something like that. Sigma equals something times strains, but including pressures now. So this is a constitutive equation that's written in terms of effective stresses, total stresses, strains, and fluid pressures. And so we should be able to substitute it in for this value. So 4 requirements. Equilibrium equation, the top equation on that page. Constitutive equation, this equation here. Displacement should be continuous, which is a requirement, and that we have initial conditions and boundary conditions to solve it. So this is the conservation equation, equilibrium in this particular case. This is the constitutive equation. We know that we can substitute this into here. We know that we have values of this. So these are the normal relationships. These are the shear relationships, which go here, which we can substitute. And we have fluid pressures also defined in terms of strains, which could go in here. And we can combine all those together. If we combine them all together, then we end up with a single equation, which is this. Actually, one equation in each direction that we have. So you'll see that you can imagine that if we substitute a value of stress into here, then we'll have an equation that includes strains and pressures. I don't know if you can still see it if it's that way. So if we substitute this into here, we're going to have strains and pressures in this term. If we convert the strains into displacements, don't have those relations on here, but well, we know that strains in the x direction is equal to dux dx, for instance. So stresses go into here. They include strains and fluid pressures. Strains we can define in terms of displacements. Fluid pressures we can define, well, we keep the fluid pressures. And so when we look at the overall expression here, which I'll bring out, you'd expect that the strains, the stresses are converted into displacements. Some of the stresses are converted into strains, which we'll leave them that way. And the fluid pressures, when we substitute these, also end up in this equation as well. And so that's the consequence of basically taking this equilibrium equation, putting in the constitutive equation, and making sure that the strains that we have here are substituted by terms like this, dux. And this is a second order derivative. So that's the governing mechanics equation. And if you remember from what we had before, we basically had a stiffness equation which operates on displacements. This is, of course, displacement 1, and has a fluid pressure term as well. Okay, it's getting small, but let's do it. So we have the solid mechanics part taken care of. The fluid mechanics part. Continuity is this. Or conservation, I guess. dv, yeah, we had this written out before. dv dx, we had rho dv dx is equal to 0. The very first meeting we had, we talked about that. So those are these terms here. So this is mass in equals mass out, or volume in equals volume out. And this is accumulation. We substitute Darcy's law into this term here, accumulation. We substitute Darcy's law into here to get this, and we end up with something that gives us this. We substitute in strains, overall volume strains being equal to fluid strains being equal to change in fluid pressure and a change in strain in the volume. If we substitute it in here, we get a term that relates to squeezing the fluid out of the sponge, which is this term here, and how the fluid changes volume as it changes pressure, and either leaves space for more fluid to come in, or if it expands, it has to leave the volume. And so from substituting this into here and here, we get this expression here. And so what we have are two expressions that have the requisite coupling in them. And so this is the solid mechanics equation, and this is flow. And so if we boil them down to what we know we had before, we could use COMSOL to be able to define these. So basically, solve the flow equation. This operates, this is similar to the storage term. This is the flow term. And this is the coupling. And so we have the magnitude of coupling in this particular case. This is the solid mechanics term, all of this. S dot M. and this is the coupling. And so these new terms are the ones that we've never seen before. And they're the off-diagonal terms. And it's interesting in that So these are now the new terms that we have to deal with. So what we could do is we could go into COMSOL and we could try solving a solid mechanics problem on its own, and in the same geometry solving a flow problem on its own. They'd run simultaneously and separately. They wouldn't talk to each other. And so long as we make sure that we include this other component, these two other components, in the way that we did for the dual porosity terms, so they can talk to each other, we should have a solution. So let's see if we can do that. It cooperated for us reasonably well last time. Let's see if I can find the right place for this. No doubt something, that was dual porosity. It's something called BO, I'm guessing. I wonder if this will work. Yeah, that looks like a good possibility. Let's do it. See if it actually works. Almost in the last stretch, I guess. And so you even got some results there. So let's see, I'll try and make sure that I don't mess this up so we can actually see something. So what did we say before? We said that if we looked at the geometries that are included, then this defines the two problems. So we have a solid mechanics part, which is here, and we have a diffusion equation or a flow equation part that's included. They both would run separately if we did nothing with them, but we could execute them together in some way. So if we go back to see what this was, so let's look at the flow part first. This is the equation we're going to want to be able to emulate. Maybe we can get them both on the screen. I know you can't see the bottom of the screen very well if I do that, because the other screens are in the way. I guess I don't want to get too fancy. Oh, that looks like it might do it. Yeah, okay, let's do it. Yeah. Slightly truncated. Now it's thinking. So I guess we don't have to do that too much. And so what we'd like to do is be able to get this part that defines the response of the flow system. It says it's not responding, but sometimes it comes back from the dead for us, has done in the past. So long as we're patient. Yeah, well, I knew that I'm not very patient anymore. So we can start it up again. It would be good if Windows did check for a solution to the problem, because it's getting a bit tiresome. Okay. Yeah, right. So you remember that we're in a system that looks at diffusion. We have these choices when we set up this mesh of defining the subdomain behavior and also the boundary. We're not so interested in the boundary here, but hopefully we can look at what the subdomain looks like. open for us and cooperate. And I think we'll find that there's going to be some term in the governing equations that allows us to put in this magnitude. If it allows us to, if it shares itself with us. And the amount is going to be. So I suppose we should make the point that what are we going to have to do for this? It may allow us to define the strains, or it may want us to define the displacements. So if we want to calculate what the volume strains are with time, then that would be the same as saying the rates of change of the strain in the x direction plus the strain in the y direction, and of course strain in the x direction is equal to dux dx. So let's see if it's decided to. No, it hasn't. Maybe it's not going to work. I don't think there's much we can do in that particular case. What we could do is this. Let's see if we can start from first principles. Oh, this has its utility. So, structural mechanics, plane strain, static behavior, at that behavior. It doesn't really have a flow system, so what we could do is use, we said before, the heat transfer works just fine. Conduction will be just fine. The essence of the behavior is transient, and so we need to add that. So we have the two modules we need. Okay. We need a geometry. It's always fun to make a fun geometry if we can. It's fun to do this. I don't advise as much to put a hole in it. I don't know why. And now we know that when we look at this, we have these two different systems. If we look at the physics, it does open. This is the subdomain. This is for heat transfer. Oh, I guess that's the one we wanted. So what we have is the flow part, conduction. We have fluid conduction. We have the capacitance term, which would be this, pressure. And we need something else. We need something that gives us, basically this is going to be a source term. All the units of this have to be in, not this Q, this is just a constant. It's different from the Q we've been using. It's a poroelastic constant. So this term has to be a Q. So in other words, what we're going to want to do is we're going to want to put something in here that represents that behavior. And so that's what we need to do. Okay. If we look at the other part, the plane strain, we can also come in and look at the subdomain settings. It doesn't have the magnitude in there. Density. So, okay, what we're going to do here. So this is now solving this expression, but it also has a term that is in here. So I suppose we have to figure out exactly what the, what are the units of this? Alpha is a coefficient which has no dimensions, and so the magnitude of this force, or this term, has to be consistent with these dimensions. So dp dx is equal to what? Pressure is in newtons per meter squared. Length is in meters cubed. So this is equal to newtons per meter. newtons per meter cubed. So this is a body force. And so the appropriate place to put the magnitude of a body force would be as an equivalent body force in the system. And I think the appropriate place would be a load. This is a body load in the x direction. And so I suppose the magnitude in the x direction would be, well, this is one equation, I should make the case. So this is the equilibrium equation in the x direction, and there'll be an equation like this for y and no z in this particular case. So dp dx would be, would just be alpha times p dp dx. So we'd want to be able to put that in, and I guess it would be negative. And so how do we do that? So I think we need to put a term in here for these body force. We want to use this. And I suppose the other thing that we want to know is what the variables are that are used in this. And okay. So actually, this is the part we couldn't see before. We talked about isoparametric elements and the order of integration. So this is using 4-point quadrature for the integration. And I'm not sure what the constraint order is, but it's using quite a high order. And so you can change those. Okay. Let me go back. Let me go here. Look at this. So let's try and dissect exactly what's happening in this. And you have to dissect it from here. It's not so obvious. But this is something we know. All right, here we go. So this is the strain in the x direction. So the COMSOL value that defines the normal strain is epsilon x. No, ux, sorry. So remember that. The strain in the y direction is Vy. Let's see if we can also, maybe we won't get it here. And look at this. So this Tx, this is the temperature. So Tx, I'll forget it if I don't write it. So let's do it. So in this, dt dx is equal to Tx, which is the equivalent, if we like, of dp dx. We said also that the strain in the x direction is equal to ux, and the strain in the y direction is equal to uy. No, Vy, wasn't it? It's not subscripted, it's actually the term Vy. So this is ux and Vy. And so I'm looking at this, I guess you can't see this. But this is a flux term. And yeah, I guess it is quite coarse, isn't it? So you can see it much less than I. So it says that the flux is equal to minus kxx, which is the conductivity, thermal conductivity in the x direction. Actually, kxx underscore ht multiplied by tx, which is the component in the x direction, plus kxy ht times ty. So those are the fluxes. And so what those magnitudes would allow us to do is, I think that's the information we need to be able to say something about the terms that we'd have to add. This says epsilon x underscore pn, which I think in their terminology epsilon x is strain in the x direction, and Pn I think is their term for plane strain module. So it's kind of apparent. And so if we know what those are, then we have a fighting chance of being able to put in the right terms. So what do we need? For the flow equation, we need a term which is alpha d epsilon v dt. That's not so easy for me to do. Let's do the other one first. For this one, we need alpha times dp dx. So in other words, alpha times dp dx. And so that would be equivalent of alpha times tx. And if we put that term in a coupling, it would allow us to be able to calculate that. If we wanted to get the term, the other term that we need is this, alpha times d epsilon v dt, then certainly that's the same as alpha, which we can define, multiplied by epsilon v, which would be mu x plus vy, and their derivatives. So I'm trying to remember how to get the derivatives of those in there. Can't remember quite offhand. So let's do the one that includes the solid mechanics part first, because I think I know how to do that. Multiphysics, plane strain, subdomain, domain, loads. We want some term that looks like alpha dp dx. We need something that goes in here. I don't know if, can you see that? Can I type this on? Alpha times ty. And so those will be the terms that go in there. Maybe a minus attached to it, I guess, depending on the sign convention, but that's essentially what it would be. We're not going to get this working, I don't think. So that's fine. The apply, I guess we can apply it. It might tell us that it doesn't really know exactly what alpha is. I suppose what we would do is we would, alpha in our case is actually going to be the magnitude of 1. So actually that's the easiest way to do it. You can just have it equal to 1, essentially equal to 1. So that would work. Okay, and so for the other part, for heat transfer, we want again the subdomain section. And the term that we're going to have to represent is going to be the flow rate. And so the flow rate has to be, the equivalent part has to be strain, which we know exactly what it is. It's going to be this. But we have to do that as a function of Ux. So I guess we could look in terms of the equations to see exactly if there's an example we can follow. That's always a useful thing to do. And so in these, I wonder if it's set up in any way to do differentiation. No, don't see the expression. I see square roots. There is a way to differentiate terms in this, and that's what we need. But I don't see offhand, and I can't remember exactly what the expression is that we need to do. And that's fine. We'll probably get the idea anyway in terms of what's going on. So basically the idea is to be able to, in these expressions, be able to put the appropriate magnitudes in for the flux. We need something in here that looks exactly like the term. Is there a way to do it? No, we still need a a time derivative with respect to t. And so, yeah, so I can't think exactly how I'm going to get this magnitude that we have down here. So I'm going to quit there because we're coming up to the end of our time. But you get the basic idea. I think it was perhaps more obvious how to do it when we talked about dual permeability systems, but it's the same idea. You have to work from the PDE, you figure out what the transfer coefficients are for these off-diagonal terms. The two off-diagonal terms we have are for these components here, which in a mechanistic way is the amount of fluid which is squeezed out or into the system by deformation, and this is the body force which is applied by the fluid pressure within the system, the body force acting on the solid mechanics part. And if we have those and we couple them in terms of some common origin, this would be defined in terms of deformations. This is defined in terms of fluid pressures, which are the dependent variables in each of these two equations. We have a solution to it. That's it. And so I'm going to leave it at that. So I think that's kind of there's some other stuff here. There's also an example of doing a one-dimensional calculation, which we didn't do in this particular case. I suppose this is a bit more relevant now that we zoomed to before. The fact that the finite element matrices that you get are a function of a second-order PDE, a first-order PDE in space, and also a zeroth order PDE. And they are very specific forms based on that. And those are the typical ones that are used. This is for porous media flow, Darcy's law. This is for mass diffusion, chemical mass diffusion. This is for thermal conduction. This is for advection in the systems. And this is for capacitance. This is for advection and also in the pore mechanical equation. We have this term like this. And this is for capacitance. And so once you know what those three operators look like, and they look like this, this, and this, then you have enough to be able to assemble the sets of equations that allow you to deal with that. And so I'm going to leave that there. So that's kind of it. I'm not really sure, I haven't really thought about what I should say, what magnificent comments I should make at the end of the day. But, basically, I think we've covered a lot of ground. So you've covered enough to be able to know lots about fluid flow. You've covered enough to know something about mechanics and be able to do something about it. And we've covered enough, I think, to be able to at least get a feel for the fact that you can make these individual behaviors run simultaneously and unconnected to each other within a program. But if you want to get the most of them in terms of the coupling, it's usually the coupling between them which is the most interesting part. In the same way that, you know, the interesting research work is the stuff that's on the boundary between different domains. Material scientists working with biologists, that's where you make the big discoveries, when you have different skill sets. I think it's the form of these couplings which is also sometimes difficult to do, unusual, but sometimes rewarding if you can figure out exactly what they are. And I think you at least have the background to be able to do that in some way. And so we'll leave it there. There's lots of other material in the notes, there's other stuff online if you want to use it, you're welcome to use it. And it's been fun being with you for a while before we all disappear in our separate directions and do our own thing, I guess, to keep our heads down. And so, yeah, so I wish you well, and I'm going to leave it at that. Right on time. Did you see that? 1:45, I guess. So anyway, that's it. That's all I have to say for you. I'm sorry that ComSol didn't work a bit better. It'd be nice if it was a little more straightforward. But I think there's something running in the background that stops it from working. Some kind of graphics card glitch that doesn't allow it to operate so cleanly. And so I need to sort that out.